All right, everyone. I am here with Arul Menezes. Arul is a distinguished engineer at Microsoft. Arul, welcome to the TWiML AI podcast.
Thank you, Sam. I'm delighted to be here.
I'm really looking forward to our chat, which will focus on some of the work you're doing in the machine translation space. To get us started, I'd love to have you introduce yourself and share a little bit about your background. How'd you come to work in NLP and translation? And tell us a little bit about your story.
Yeah, so I've actually been at Microsoft 30 years at this point.
Wow.
I know. Oh, God, it's a long time. I was actually in a PhD program. I came here for the summer, loved it so much, I never went back. So I worked at Microsoft in the various engineering teams for a while, and then eventually I drifted back into research, and I joined the natural language processing team in Microsoft Research, and I started the machine translation project. And I've been doing that ever since. I've been doing machine translation for like 20 years now, and it's been a great ride because it's just a fascinating field, so many interesting challenges, and we've made so much progress from like when we started, and we've gone through so many evolutions of technology. It's been a great ride.
Yeah, there are some pretty famous examples of how the introduction of deep learning has changed machine translation. I'm assuming that your experience there is no different. Can you share a little bit about how the evolution that you've seen over the years?
Sure. I mean, historically, machine translation is something people tried to do, in the 50s. It was one of the first things they wanted to do with computers, along with simulating sort of nuclear sort of bombs. But for the longest time, it was very, very hard to make progress. So all the way through, I would say, the late 90s, early 2000s, we were still in sort of rule-based and knowledge sort of engineered approaches. But then the first real breakthrough that came in the late 90s, actually starting a little earlier in terms of some papers published at IBM, but really taking off in the late 90s and early 2000s was statistical machine translation, where for the first time, we were able to take advantage of like large amounts of previously translated data, right? So you take documents and web pages and things that have previously been translated by people, and you get these parallel texts, which is let's say English and French, and you align documents and sentences and then eventually words and phrases, so you can learn these translations. And so with statistical machine translation, we were learning from data for the very first time instead of having people hand code it, and it worked actually astonishingly well compared to what we were doing before. But eventually we ran into the limits of the technology because while we had the data, we didn't have the techniques to do a good job of learning what that data was telling us, because the machine learning techniques that we had back then just weren't good enough they were good at memorizing, right? They could if you said something exactly the way they had seen in the data, they would do a good job of translating it. But they were terrible at generalizing from what they saw in the data. And that's where neural models come in. Like, neural models are amazing at generalizing, People always talk about how some of the latest models, you can probe them to figure out what was in their training data and get them to reproduce what was in their training data. But what we forget is it takes work to actually make them do that, because most of the time they're generalizing, they're paraphrasing, they're not just replicating their training data. And that's something we were not able to do before. So if you look at the evolution over the last 20 years of machine translation, we had our statistical machine translation, which did really well for a while, but then eventually plateaued. Then, we had sort of the advent of neural networks. And the first thing that people tried to do was, we did feed-forward neural networks. We tried to shoehorn them into the framework we already had and combine sort of feed-forward networks and statistical techniques. And that worked okay. You got a few incremental improvements. But it wasn't until we had the sort of pure neural LSTM models that we, for the first time, were really capturing the power of neural models, right? So what an LSTM model would do would be, you have this encoder that you feed the source language sentence in, and it basically embeds the meaning of that entire sentence in the LSTM state. And then you feed that to a decoder that is now generating a fluent sentence sort of based on this very abstracted embedded understanding of what the source language said. And so that's very different from the way we were doing it, just sort of copying words and phrases that we'd memorized. So that was the first revolution, and it gave us amazing results, actually, compared to what we were doing before. And then, of course, along after that came transformers, which sort of take that whole encoder-decoder architecture, but take it to the next level. Instead of having the meaning of the entire source sentence be encoded into a single LSTM state, which may work well for short sentences, but gets worse as you get to longer sentences. In a transformer, we have the self-attention that's basically looking at every word in the source and every word in the target, and so you have like full context available to the model at any point in time. And so that's where we stand today. Is transformers are the state of the art, but of course there's lots of really cool, interesting variations and things we're doing, which I think we're going to talk about at some point.
And when you talk about transformers being the state of the art, is that what is powering the current kind of production Azure machine translation service, or is that the state of the art in research? And there's some combination of the various techniques you mentioned that is powering the live service.
So the live service is very much powered by transformers. We have all 180 language pairs or something that we support, powered by transformers running in production. Now, one thing we do is that we take advantage of what's called knowledge distillation, right? To take the knowledge that's embedded in these very large transformers that we train offline, and then condense that or distill that into smaller, still transformers, but smaller, shallower, and narrower models that we use in production, right? So we typically go through multiple stages of these teacher models before we get to the student. So our pipeline is actually fairly complex. We take the parallel data, which I mentioned earlier, which is sort of the lifeblood of machine translation. This is the previously translated human text. And we train like a first teacher based on that data. Then we typically do what's called back translation, which is a technique in machine translation to take advantage of monolingual data. So data that's not parallel, so it's not translated source and target, it's just in one language, typically the target language. And what we do there is we want to take advantage of this monolingual data to teach the model more about the syntax of and the semantics of the target language, so it gets more fluent. And the way we incorporate that data into a machine translation model is to something called back translation, where we take the target language data, we translate it back to the source using one of our models, and then we use it to train the model in the other direction. So this is a little complicated. So basically, if you're training an English to French model, in addition to the parallel English French data, you also take some French monolingual data, you translate it back to English using your other direction translation system, the French to English system, and then you put that synthetic data back into training your English French system. Okay. So so that's
essentially a data augmentation technique.
It is, yeah. It's a data augmentation technique, and it works like incredibly well. Actually, adds several points to our metric. The metric we use in machine translation is called the Blue score. I mean, there are other metrics, and I could talk about that at some point if we want to get into it. But we get several points of Blue score out of the back translation. And then, so that's our final sort of teacher model, which is typically huge. And then what we do is we we use that model to teach the student model. And the way we do that is essentially we run like a huge amount of text through this teacher model, and then we take the data generated by the teacher and we train the student on it. And the reason that works is because unlike sort of natural data that we train the teacher on, which can be confusing, contradictory, diverse, the data generated by the teacher is very uniform and it's very standardized. And so you can use a much simpler student model to learn all of that knowledge from the teacher, because it's a simpler learning problem. And having done that, that model runs like super fast, and we can host in production and translate like trillions of words, so yeah.
And so the student teacher part of the process is interesting to explore a little bit further. Are you essentially trying to do something? The task that you're trying to, or goal that you're trying to achieve with that, is model compression.
Right.
It's a very different approach to it than like pruning or some of the other ways you might approach compression.
Yeah. Right. Yeah, so we do we do a lot of different things for model compression, right? So one of the things we do is we do quantization, for example. We run all our models in 8 bits. We've experimented with less than 8 bits. It's not quite as effective. But we do that. We do some other like pruning techniques as well. But the biggest one is the knowledge distillation. And what you're trying to do there is get a smaller model to basically mimic the behavior of the big teacher model, just running a lot cheaper. And by combining all the techniques, we published a paper last year on this at a workshop, and from our big teacher with all of the knowledge distillation, the compression, the quantization, and so on, we're running something like 250 times faster on the student than the teacher. There is a small loss in quality, right? But we lose maybe half a blue point, not too much. And in some cases, not even any. We can actually maintain the quality as is. So
my next question for you, the way you describe the process, and in particular, the idea that the teacher is outputting more consistent examples than what is found in the training data.
Right.
My next question was, or the intuition that I had was that would cause the student to be far less effective at generalizing and would make it perform worse. But it sounds like that's not the case in practice.
So the key to that is to make sure that the data that you feed through the teacher to teach the student is diverse enough to cover all the situations that you may encounter, right? So the students are a little weird. And I think you're sort of hinting at that. We do, for example, overfit the student to the training data, which is something that you typically wouldn't do in your teacher model, because you, in fact, are trying to make the teacher match the student as much as possible. So some of the things that you do to make the teachers better at generalization, you don't do in the student. And in fact, if you look at the student distributions, they're much sharper than the teacher distributions, because they have overfit to the data that they've seen. But there's a little evidence that you could get into some corner cases that are brittle, there's this problem of neural hallucination that all of the neural models are subject to, where occasionally they'll just output something that is completely off the wall, unrelated to anything that they've seen. And there's some evidence that there's a little bit of amplification of that going on. Like if it's, the teachers are also subject to hallucination, but maybe at a very, very low frequency, and that maybe that's being amplified a little bit in the student. So we're working on managing that, but yeah, so there's it's a trade-off. Like the students have lower capacity, but that's what enables us to run them. And we run them on CPU. We don't use GPUs in production inference. We use, of course, all the models are trained and all the knowledge distillation are done on GPUs. But in production, we're just using CPUs.
And is that primarily based on the cost benefit analysis, or is it based on the latency envelope that you have to work with and not wanting to kind of batch
Right.
inference requests?
Yeah, that's exactly right. I mean, latency is a big concern. Our API is a real-time API, and so latency is the biggest driving factor. And honestly, if you do inference on GPUs, it's you get some latency benefit, but the big benefit is on large batches. And so, unless you have a matched batch translation API, you can't really take advantage of the full capacity of your GPU. So, in a real-time API. Yeah.
Mm-hmm. And are both the teacher and the student models transformers?
Yeah, they are. Yeah, the students are, transformer large or a little bit larger, and then that's the teachers, and then the students they're very highly optimized transformer. I mean, we start with transformer based, but then we do a lot of really strange stuff. I would refer you to the paper, actually.
Okay.
Yeah.
When you were describing the data augmentation technique that you use,
right.
It kind of called to mind ideas about incorporating a GAN type of an approach where you're doing the pass back translation, and then maybe there's some GAN that is trying to figure out if the result going backwards is like a human translation. Is there a role for that kind of technique? Is that something that comes up in the research?
Yeah, so we've looked at GANs. There were some exciting results, but in the end, I mean, I think we have some okay-ish research results. We haven't seen much benefit, but more broadly, in terms of data augmentation, we're using it all over the place, right? So we have the back translation, but there are a lot of phenomenon that we want to address in machine translation that is maybe not well represented in the data. And so we use data augmentation pretty heavily to cover those cases, right? To give you a simple example, when you translate a sentence and you get a particular translation, and then you go in and let's say you remove the period at the end of the sentence, sometimes it changes the translation entirely. They may both be perfectly good translations, right? But they're different. And so one way to look at it is, well, they're both good translations, but people don't like that. So if you look at our customers, and we're very sensitive to what our users, the feedback we get from our users. So one of the feedback we got was that we want a little more stability in our translation. So just because I lost the period at the end of the sentence, I shouldn't get a drastically different translation. And so it's very easy to augment the data and say, well, stochastically, I'm going to delete the period on my sentences, and so then the model learns to basically be robust to whether there's a period or not. Now, of course, that's different with a question mark. You definitely want to leave the question mark in because that changes the meaning of the whole sentence. But, things like that, punctuation, the period, commas, things like that. Maybe, capitalization. For example, one of the other examples would be like an all caps sentence. You take the whole sentence and you change it to all caps, you get a totally different translation, right? So we again generate some synthetic all caps data so that the model learns to do a good job of translating that as well. And then there's all these I would call them long tail phenomenon that we feel that data augmentation is a good way to address some of these.
That your examples are really interesting to me because I'm comparing them to your textbook NLP types of examples where the first thing you're doing is making everything lowercase and getting rid of all of your punctuation.
Yeah,
sounds like that does not work for translation.
No, because there's a lot of information in casing and punctuation, right? If you want to handle names, for example, you need to pay attention to the case of the input, So there's like everything in the input has information. And so actually even the punctuation, right? Like sometimes if you take the period off at the end of the sentence, it should change things because it may be a noun phrase rather than an actual sentence, right? So it's not so much about pre-processing the data and trying to be clever. It's about exposing the model to different variations so that the model can figure things out for itself.
Mm-hmm.
Yeah.
One of the questions this prompts is like the unit of, work, or the unit of thing that you're trying to translate.
Right.
Translating a word being different from translating a sentence, being different from translating an entire document.
Right.
It sounds like most of what we've been talking about is kind of phrase by phrase now relative to the word by word that we were doing 20 years ago.
Right.
But are you also looking at the entire document? Are you able to get information from a broader context to impact the translations?
Yeah, so that's a very good question, Sam. Yeah, so the context matters a lot, right? So one of the reasons why neural models are so great at translating now is because they are looking at the whole sentence context, and they're translating the entire context, the sentence, and they're basically sort of figuring out the meaning of every word and phrase in the context of the whole sentence, which is something we couldn't do with statistical machine translation before. So now the next step is to expand that context to beyond the sentence, right? So there are a lot of phenomenon that it's impossible to translate well without context beyond the sentence, right? In many languages, unless you have a document level context, a paragraph level context, you can't generate the right pronouns because you don't actually know, the sentence doesn't have enough clues to let you know what is the gender of the subject or the object or the person you're talking about in that sentence. Beyond just the pronouns, it's also like the senses of words and disambiguating those. So we're actually moving towards translating at the whole document level context, or at least very large multi-sentence fragments, and then there we'll be able to use the context of the entire document to translate each individual sentence. And we actually have some really great research results based on translating at document level. So we're pretty excited about that. That model is not in production yet, but it's something that we're working on. We did ship a document level API. I think it's in public preview right now, which addresses sort of the other half of the problem, which is, people have documents, they've got formatting, it's in PDF, it's in Word, it's in PowerPoint, whatever, and HTML. And it's a hassle getting all the text out of that, getting it translated, and then we're still trying to reassemble the document and reconstruct the formatting of that document on the translated thing. So we've made that easy. We just ship this API. You just give us your PDF. We'll tear it apart. We'll do the translation. We'll put it back together, and we'll preserve the format. Especially for PDF, that is actually really hard. Doing the format preservation is tricky, but we're pretty excited about that API. And so then that's the place where our document level neural model would fit right in, right? Because now we have the users giving us the whole document. We can not only handle all this stuff about the formatting and all that, we can go one better. We can actually use the whole document context to give you better quality translations.
Mm-hmm. Can you give us an overview of some of the techniques that go into looking at the entire document when building the model?
Yeah, so right now, as I said, we haven't actually shipped this, so we're looking at a bunch of variations. There's several things that people have looked at, like there are hierarchical models where you run transformers at the sentence level, and then you run a second level to sort of like collect the sentence level information into like a document level context vector, and then you feed that back into translating each sentence. I mean, we're finding that actually, if you just make it like super simple and treat the whole thing as if it were a giant sentence, in effect, you get really good results. You do have to deal with the performance issues, right? Because transformers are n squared in the size of the input and the output. So instead of handling a 25-word sentence, if we're now translating 1,000-word document or paragraph, then that's you've got like an n squared problem in terms of the performance, right? It's going to be that much more expensive. But we have things that we're looking at to make that faster as well. So we're pretty optimistic we can do that. And I think we can do that with just letting the transformer figure it out for itself, rather than trying to be very clever about all this hierarchical stuff.
Nice.
Yeah.
Let's talk a little bit about the role of different languages. So we've already talked about how you can use back translation to help augment the performance of your the translation of a language in one direction, or the translation between a couple of language pairs.
Correct.
Are there ways to take advantage of the other 130 or so language that you support when you're building the N+1 model for a given language?
Absolutely. That's been one of the most exciting things, I would say, that came out of sort of transformers and neural models in general, is the ability to do this sort of transfer learning between languages, right? And the reason we can do that is because, transformers or neural models in general are representing the meanings of words and sentences and phrases as embeddings in, this space. And by training on multiple languages together, you can actually get the representations of these languages to merge and have the similar concepts be represented through, basically related points in that space, right? So as a practical matter, we've basically found that if we group languages by family, right, and so for example, we took all our Indian languages and we put them together and we train one joint model across all of the languages. And now we're talking, languages where you have a very different amount of data. You have Hindi, where we have quite a lot of data, and then we have like Assamese, which is, I think, the last one that we shipped, that has, probably like 2 orders of magnitude less data. And the wonderful thing is that by training them jointly, the Assamese model learns from the huge amount of data that we have for Hindi, and does like dramatically better than if we had just trained on Assamese by itself. In fact, we've done those experiments, and for the smaller languages, we can get like 5-10 blue points, which is like a crazy level of improvement.
Wow.
Just from the transfer learning and multilingual. We also do that with like Arabic, all of our Middle Eastern languages. So we're just like grouping more and more language families together and getting huge benefits out of this.
And when you're grouping the language families, do you experiment with going across language families and seeing if there's some improvement there?
Yeah, so we've trained models that have like 50 or 100 languages in them. What you run into is, as you add languages, you have to increase the size of your vocabulary to accommodate all of these languages, and you have to increase the size of the model, because at some point you run into model capacity limits. So you can have a model that does a really nice job of learning from 50 or 100 languages, but it gets to be a really huge model. And so in terms of cost effectiveness, we've found that like you get like almost all of the benefit of the transfer learning at like a much reduced cost by just grouping, 10, 15 languages at a time. And if they're related, it's better. But actually, even if they're unrelated, it still works. It's quite amazing how well it works, even if the languages are not related. Yeah.
You may think of it as like a computational test of Chomsky's universal grammar, and these ideas that suggest that all languages have these common elements.
Yeah.
If you are able to train these models across languages and improve them, that would seem to support those kinds of theories.
I mean, definitely the models do a really good job of bringing related concepts together in the embedding space, right? Yeah.
And so would you consider this, you reference this as like multilingual transfer learning, would you also think of it as a type of multitask learning as well, or is that not is it not technically what you're doing in this task?
So we're also doing, in addition to multilingual, just machine translation, we're also doing multilingual, multitask learning. And what we're doing there is we are combining the sort of, so there's, let me back up a bit. There's been this whole line of research based on models like BERT, right? Pre-trained language models, where if you look at BERT, it's actually the encoder half of a machine translation model, but it's trained on monolingual data. It's trained on a single language data on this objective that's a reconstruction objective, where you're given a sentence where you have a couple of words or phrases blanked out. You need to predict that, right? Mm-hmm. And then you have multilingual BERT, where you take multiple separate monolingual corpora, right? So it's like a bunch of English text, a bunch of French text, and all of that, and you train them jointly in the same model. And it does a pretty good job of actually pulling the representations of those things together. So that's one line of research that's sort of really driven a revolution in like the whole natural language understanding field, right? So, for example, today, if you want to train a named entity tagger, you wouldn't start from scratch on your named entity data. You would start with a pre-trained model. So one of the things that we're very excited about is we have this project that we call Z-Code, where we're bringing the machine translation work and this sort of pre-trained language model, BERT style work together, right? And we're training this multitask, multilingual model that's architecturally, it's just a machine translation model, right? But in addition to training it on the parallel data, let's say the English-French data and the English-German data, and conversely the German-English data and the French-English data, and 10 or 15 or 50 or 100 other languages. In addition, we have a second task where we have the BERT tasks. We take monolingual data and we have it reconstruct, the missing words. And we also have what's called a denoising autoencoder task, which is where you give it a scrambled sentence and then it has to output the unscrambled sentence through the decoder. And then now you have these three tasks, and we train them in rotation on the same model. So they're sharing parameters. So the model has to figure out how to use the same parameters to do a good job of the BERT task, to do a good job of the denoising autoencoder task, as well as to do a good job of the machine translation task. And this, we find, leads to like much better representations that work for better natural language understanding quality, but also better machine translation quality.
Nice. And the BERT task in this example is within the same language as opposed to
right
across the target language.
Yeah, there's actually like a whole family of tasks, right? I mean, people have come up with, we've experimented with like 20, 25 tasks, right? So you can do a monolingual masked language model task, which is the BERT task, but you can do a crosslingual masked language task as well. And you can do the denoising autoencoder task monolingually, where you have to reconstruct the same language. But you can also do that crosslingually, where you have to reconstruct sort of a scrambled foreign language task. So there's like a real like sort of stone soup approach here, where people are just throwing in all kinds of tasks, and they all help a little bit. But it's this. We need to figure out like what's the minimal set that you need, because it's work, it's computational expense to train these huge models on all these tasks. So if we can find the minimal set that works, that would be ideal. And so far, what we're working with is like a denoising autoencoder, a masked language model, and a machine translation task.
Mm-hmm. Very, very cool. Very cool. One of the things that I think as users of machine translation we run into is that it works great in kind of these general contexts,
right?
Kind of everyday language. But when you start to get into specific domains,
right,
it's a lot harder for the systems to keep up. Is there any work that you're doing in that area? So I think one of the things that often users of these kinds of machine translation services experience is that they work great in the general case, but when you start to try to apply them to specific domains, it's a lot more challenging, and kind of the technical conversations, or translating, medical conversations, or, construction, or what have you. Yeah. Is there anything that you're doing to make the domain specific performance better for these kinds of systems?
Yeah, definitely. Domain performance in specialized domains is a real challenge, and we're doing several things to get better there, right? So the first thing is that the quality is really determined by the availability of data, right? So in the domains like, let's say, news or web pages where we have a ton of data, we're doing really, really well. And then if you go into a more specialized domain, like, let's say, medical or legal, where we don't have as much data, we're maybe not doing quite as well. And so one of the things we're doing is we're now taking the same neural models that are good at translation, and we're using them to identify parallel data in these domains that we can find on the web that we maybe weren't finding before. And we can do that because these models, because the representations are shared in the multilingual models, they're actually very good at identifying potential training data that is translations of each other. So that's one thing we're doing. The other thing we're doing, of course, is the same kind of transfer learning approach that we're using cross-lingually applies within domains as well, right? So if you have a small amount of medical domain data, you don't want to just train a model that's based just on that small data. What we're doing instead is we're taking our huge model that's trained on a ton of general data across a bunch of domains, and then you fine tune it for the specific domains that you're interested in. And we actually have a product called Custom Translator that we have thousands of customers using, where they are using this approach to customize the machine translation to their company or their application needs, right? So let's say you're a car company or something, and you have a bunch of data that's about automotive manuals, right? So you come to our website, you log in, you create an account, etc. You upload this data, and then what we do is we take your small amount of domain-specific data, we take our large model, and then we fine-tune it to that data, and now you have a model that does sometimes dramatically, again, 10, 15, 20 blue points better than the baseline, because we've learned the vocabulary and the specifics of your domain, but we're still we're standing on this platform of the broad general domain quality. So that's been extremely popular and valuable, actually. We just shipped a new version of that based on transformers a couple of months ago.
And in that case, the user is presumably bringing translated documents so that you're able to train or fine-tune with both source and target translations?
Yeah, that's exactly right. I mean, a lot of the companies that we work with have some data, right? Like, let's say they had a previous version of their vehicle or, whatever, and they had manuals that were translated. In Microsoft's case, for example, we have, let's say, the manuals for Microsoft Word going back, a couple of decades. And this is the kind of data you can use to customize it so that anything, any new content that you want to translate can have a very consistent vocabulary and tone and so on. Yeah.
Mm-hmm. And in that first example, or the first technique that you mentioned, that sounds really interesting. So you've got this this index of the web in Bing,
right,
for example, or maybe you have a separate one, but have this mechanism to kind of crawl the web. And it sounds like the idea is that you can use the model to identify, hey, I've got these two documents. They look really similar, but there is a high percentage of words that I don't know that occupy similar positions in the same documents.
Yeah.
And then you have someone translate actually, then once you know that, you can just align them, so to speak, and you've got a more domain-specific document to add to your training set. Is that the general idea?
Yeah, I mean, it's like you're trying to find two very similar looking needles in a very, very, very large haystack, right? So you have to have a magnet that finds exactly those two needles and rejects everything else. So the crosslingual embedding space is pretty key here, right? So you basically, in principle, if you embedded every single sentence or document on the web, and then we're able to look at every single document and find all of its very similarly close embeddings, you'd be done. But that's
easier said than done.
Easier said than done, right? So that's the kind of thing that we're trying to do at scale, right? Is like you got these trillions of documents, and we want to find the matching ones. You need to do it efficiently, and so there's a lot of clever engineering that goes into like indexing this stuff and like computing the embeddings efficiently. And of course, also we're not really trying to match every page on the web to every other page on the web, because you have a lot of clues that says where if I have a document here, is it likely to have a translated document somewhere? It's going to be either in the same like top level domain or related sites, things like that. So there are ways to constrain that search.
Mm-hmm. Yeah. Our conversation thus far is focused primarily on text translation. Are you also involved in voice translation?
Yeah, so we actually have been doing speech translation for a while. Several years ago, we shipped a feature for speech translation in Skype called Skype Translator. It was, really well received, super exciting. A lot of people use it even today, right? Especially, people talking to their relatives in another country. And so there's a lot of interesting challenges in speech translation, because it's not that you just take the output of a speech recognition system and then just pass it to machine translation, right? There's a real mismatch in what comes out of speech recognition and what is needed to do a good job of translation, because of course translation's expecting well formatted text, capitalization, punctuation, sentence breaks, things like that. So we put a lot of effort into bridging that gap, post-processing the output of speech recognition so that we have, really accurate sentence boundaries. So that matters a lot. I mean, you break a sentence in the middle and you try to translate. Like if you break a sentence in the middle, the speech recognition itself is okay, because as a human reading it, there's a period in there, you just ignore it and move on. But the machine doesn't know that, and so when you're trying to translate it, you've got these two separate sentences, and then it does a terrible job of it. So getting the sentence breaks right, getting punctuation right, and so on is really important. And so that's what we've been doing. We actually have a project going on now with the European Parliament, where they are going to be using our technology. Well, there's three contestants or three bidders in this project, and so there's a evaluation that will happen in a few months. But we're hoping that they'll adopt our technology for live transcription and translation of the European Parliament sessions in all 24 languages of the European Parliament, which is super exciting.
Oh, wow.
Yeah.
So when you think about kind of where we are with transformers and some of the innovations that we've talked about, and relative to your 20-30 years in this space, and I'm curious what you're most excited about and where you see it going.
Yeah, I mean, the pace of innovation has just been amazing. There's so many things that are happening that, like, would be a really dramatic impact, right? So one is just much larger models, right? Like, as we scale up the models, we see continual improvements, and so as the hardware and the our ability to serve up these larger models keeps growing, the quality will also keep growing, right? The architecture of these large models also matters, right? Like, it's not just a matter of taking the smaller models and scaling it up exactly as is. So there are things like mixture of experts models that, for example, allow you to scale the number of parameters without the cost scaling as linearly, right? Because you have parts of the model that specialize in different parts of the problem. And then, multilingual is definitely the future. Pre-trained models is definitely the future, right? So like, if you put that all together, like pre-trained, multilingual, multitask trained, maybe with mixture of experts, huge models, and then we would specialize them for individual language pairs or groups of languages, and then distill them down to something we can ship. So, that's one area that there's a lot of innovation happening. The other thing is that, 10 years ago, people were just amazed that translation worked at all, right? And now we're doing a really good job, and the expectations have risen. So you get to the point where a lot of sort of smaller, let's call them long tail problems, start to matter a lot, right? So if you look at translation of names, we probably get them 99% right? But, a few years ago, it would have been fine to say, hey, we're 99% accurate on names. But maybe now that's not good enough, right? Like, 1%, screwing up 1% of the names is not acceptable. So, how do we get that last 1% of names? And, I'm just making up it may be 99.9%. You're still going to have upset customers if you get, 0.1% of your names or your numbers. Numbers are even worse, right? Mm-hmm. Like, if you misstate a number, even like 0.1% of the time, it could have catastrophic consequences, right? So that's an important area. I mentioned neural hallucination before. That's something we see where, again, it may happen only 0.1% of the time. But if you get like a completely unrelated sentence that has nothing to do with your input, but is really fluent, it's pretty deceptive, right? Like, because especially if I'm just putting my faith in this translation and I don't understand the source language at all, you'd be like, oh, sounds okay, and move on. But maybe it says something completely different from what the source said, right? And so that's a challenge. Mm-hmm. Yeah, I mean, there's lots of really cool things happening in this space.
Awesome. Well, Arul, thanks so much for taking some time to share a bit about what you're up to. Very cool stuff.
Thank you. You're welcome, Sam.
Thank you.
Happy to be on the show. Take care. Bye.
Thank you.